Right. So, a few things before getting back to talking about skating. The first is that the book is now available. I should have emailed. I tried to email all of you. Hopefully you got that. For anyone who hasn't discovered it yet, you obtain the book or access to the book by going to UVA Colab site for this class. This is about the only thing we do on UVA Colab, and clicking on the UVA Bookstore Access Program link, and it will take you there to obtain a 10-character code that allows you to access the book. You will be charged for this by the bookstore, and then you go to the Wiley Plus site, the actual publisher's site, and using that 10-digit code and the 6-digit code for this class, which is on the home page, for the real home page. Let me just show you this page again. There it is. So this is the website I maintain on my own server. And again, to remind you, a key link that you may want to go to occasionally is this schedule link that I'm circling with the mouse. That has today's class. Here we are, January 15th. We're going to be continuing skating. And I put in after the last class, I put up a video of the class linked to this 2020, yesterday's class link. So if you miss a class, you can go watch them. Obviously I'll put them up after, not before class. But anyway, let me go back to this page. So keep track of the schedule. It has, for example, the problem set due times on it. So the first problem set is due. Here it is, PS1. It's due on January 29th, so 2 weeks from now. You've got a while ahead. What I wanted to show you is that once you get UVA digital access to the book, you can go to the Wiley Plus site here, which is the publisher's site, my publisher's site, and using that code, which identifies this class, you can get connected. And a huge number of you have already done that, so hopefully it's straightforward and everyone will get connected. So the one other thing I wanted to show you on this page before folding it up is you guys were great last class asking questions. That's the traditional way in which this class works. It's had some hiccups in recent years because it's easy to get panicky about speaking up in a group of more than a couple people, unfamiliar to you, right? So some of you did, yay, okay? However, some of you will never be able to bring yourself to do that, and so I made it so you can ask me questions digitally. So those of you who just don't want to talk or don't want to identify yourself, there's a link down here that says messaging. See this thing right here? Woo! If you click on that, you can type a message in here, whatever, and I'll see it over here, okay? And I will try to pay attention to that screen. So if you want to send me notes, questions during class, that's a path to doing it. And if you can't remember the URL for this website, it's on those syllabus sheets that I handed out, or if you don't have one, get one. Any questions about this stuff yet? Things that you're wondering about here? Okay, I'm going to stop. Anything else logistically that I want to talk about? Not really. Okay, so the physics territory that we're in right now is in the context of skating. So it's basically answering the very simple questions about a skater's motion. And so far I've looked at a skater that's not being influenced by the world around him or her. A skater at rest tends to stay at rest. And a skater that happens to be moving tends to keep moving, and more specifically, tends to keep moving in a straight line at a steady pace. And so these are just simple observations about a skater's motion. And the reason I've got a skater in this story is because the world is filled with complications that make the simple physics, that mask simple physics. And by putting a skater on ice or on wheels, I get rid of one of the nuisances, which is friction. And so in these early days, I wanted to get rid of sort of as many of the nuisances of real life as possible. I mean, they're important, of course, but set them aside to get this to get started. So we set aside friction. For the moment, we set aside gravity. How did I do that? By working on a flat sheet of ice or a flat skating area on roller skates, whatever. We make gravity, although present, not important. We're also, actually for the whole semester, this semester, we'll get rid of air resistance. Air resistance comes up in the fall version of this class. We talk about how air affects things. Many of those effects very interesting, but right now we'll set aside air resistance. So we're just working with the world of sort of as simplified as we can get it. And having done that, I got as far last time as talking about how really skaters or any object that's at rest and it's not being bothered, and I haven't really talked about what bothered is, just it stays at rest. And I don't know where physicists came up with this expression, at rest, but it's just classic. It comes out of my mouth whether I like it or not. So it just means motionless, okay? Not moving. And so a skater or any other object at rest tends to stay that way. And a skater or any other object that's already moving tends to keep doing that same kind of motion. And we need to pin down what that same kind of motion means. Roughly, it is straight line and steady pace. All right? Well, what I wanted to do right now, starting off, is to address two sort of misconception issues that are around. And to do that, starting off, I will reach a little forward in time to 20 minutes from now and to language that I haven't developed yet properly. So I'm going to be a little bit cavalier here. Incidentally, there are some of you in this class that took the previous semester, Physics 1050, and this is review for you, and for a little while, great, review, and then we'll diverge. So bear with me if you see the same things you've seen before. Okay, two misconceptions, or two, I'm separating them into two, and if I anticipate ideas will come to in 20 minutes, I have to do it. It's hard to, there's a chicken or egg problem here. Anyway, the first misconception we dealt with last time, so these are all around inertia. And inertia is something you've heard the word your whole life in all likelihood. You've heard these expressions like an object at rest stays at rest, an object in motion continues in motion. But really, what do those mean? They're just, they're catchphrases, but what they mean matters. And so I'm hoping to convey to you really what they mean. And to also make sure you stare at the misconceptions that it's so easy to have. In fact, it's natural to have. The first one I did last time, I asked you whether you can cut grass with a rotary lawnmower, or whether a rotary lawnmower, which has a rapidly turning blade, can it cut the grass if the grass has no roots? If it's just the grass is just for some reason just sitting there sticking up, resting maybe on pavement. And more than half of you felt that probably not, that you probably couldn't cut it. And in fact, that's not true. And a demonstration I didn't do last time, so I'll just do it this time anyway. So here's my grass. It happens to be green linguine. And here's the rotary lawnmower, and now don't worry, I'll be safe. I've never injured anybody out there but one of the best demonstrations we ever did that was firing apples with a cannon across this table against that wall at about 200 miles an hour. There was a demonstration that, well, there still is, like that, but not with apples anymore. The apple hit the wall and turned into applesauce. And this whole arc of the room wore applesauce that day. Okay, but I don't do that anymore. So the point being here, that these grasses don't have to be attached to anything. They are objects at rest, staying at rest. I have to hold them up temporarily because otherwise they'll just fall over. But I can cut them with a blade, no trouble. And that's what a rotary lawnmower does. It comes upon these pieces of grass, blades of grass, grasses, and There are objects at rest that will tend to stay at rest if you don't bother them. Again, I need to tell you what bothering means. You don't influence them. The blade can just sneak right through them. It's not perfect because the blade doesn't perfectly sneak through it. They're aware the blade's there. They are experiencing a little bit of those influences from the blade. Pushes and pulls from the blade. Technically known as forces. The blade does exert some forces on the grass, but those forces are weak compared to this tendency to stay put, if you do it right, and the blade just goes right through them. Okay? So the world, it turns out, is full of instances in which you take advantage of that fact. And to show you other ones like that, this is a familiar one. You can take a sheet, you can hold the roll and you can pull the sheet off, right? You've done that. But you don't actually have to hold the roll. You can just pull really fast. And why did that work? Surely you've done it. Why did it work? It's because this is basically an object at rest tending to stay at rest. If you don't exert significant forces on it, it's going to stay at rest. And so what I did was I yanked on the sheet, on these loose sheets, so suddenly and so fast that I did influence them. I made them come with me. But they were not able to influence the roll and make it come with them. And the details will come to in such and such, but you do use this tendency of things to stay put frequently in your daily life, but now hopefully you'll be a little bit more aware of them. Okay? So you can punch stuff. You can punch a bunch of paper there, even though it's not rooted in the ground. How am I able to hit it and all that stuff? Its tendency is to stay put. So as long as I don't push on it very hard, it pretty much stays put. Okay? So that's probably the more straightforward misconception. Maybe surprising observation about the world is that things that are at rest tend to stay there for their own just because that's their nature, not because something's holding them. You don't have to tie them down. All right, the other real misconception that I want to go after, and it will become more relevant as we go on here today about skating and finish with skating, is the idea that when you do push on something, what is its influence? And you grow up making the following observations about the world around you. This is just experience. Is that if you push on something, it moves. And if you stop pushing, it stops. That's just it's not wrong, but this is an observation about things in the world that it's problematic in terms of physics, and I'll explain that in a moment. So it sure seems like things move when you push them and stop when you don't push them. Surely familiar to everybody. Well, from that you can conclude, and people did, that the pushes, technically known as forces, that forces cause motion, and that the absence of forces leads to things being stopped. That would be a straightforward conclusion to make, and it's the conclusion that basically everybody made up until approximately Galileo and Newton, that forces seem to cause things to move. Turns out not to be the correct assessment of the real world. It turns out that what forces do is change how things are moving. It makes them speed up or slow down or turn. It doesn't cause them to move directly. And so where does that tie into what I've been showing you up until, was showing you last time? It's that things actually, once they're moving, they keep moving because of inertia. That you don't have to keep pushing things to have them keep moving. They do that naturally. So why didn't it work in the case of this little puck? It's because I wasn't the only thing pushing on the puck. What else is pushing on the puck that I'm trying to ignore? Friction. So if I turn the puck on, it's got batteries and a fan inside, so now it's sitting on a layer of air. Now if I push it, and again, things aren't perfect, this table's never perfectly flat and so on, but if I leave it alone, it tends to stay, object at rest, staying at rest. If I push it, it goes from being an object at rest to being an object moving. And once it's moving, it keeps moving for free. I don't have to keep pushing. I mean, again, it's like, the floor would be better if it weren't covered with linguine. So that continued motion, I'm not pushing it anymore. It's moving, not because I'm pushing it, but because no one's stopping it. It keeps doing what it's doing. So if you can internalize that and really get it part of your worldview, the fact that objects that are moving move not because things are pushing them, but because nothing's stopping them. If you can get that in your, really in your gut, we've made progress. I mean, that's a good thing. That's a crucial part of sort of basic physics. In my experience, not everyone gets that. No matter how, not everyone gets it, particularly from classes once you calculate everything. All the calculations in the world will not necessarily change your worldview about how things move. So all the stuff that you see going by here on McCormick Road, the people on the scooters or bicycles or cars or walking or running or whatever, once they're moving, they keep moving for free. Everything about the motion, so you're running along like this, the job of your legs and stuff is not to keep you moving forward approximately, but rather to allow you to keep coasting forward. You're actually coasting, meaning that you're moving as inertia had in mind for you. It's hard to do that with your legs, but the wheel helps. The wheels help. So I could be on skates, but okay. So I'm moving forward not because something's pushing me forward, that is to your right, but because nothing's stopping me from moving forward. I just keep doing what I was doing. Inertia. All right? So big harangue about a little idea, but it's a huge idea, and that it took humankind so long to figure this out, it indicates how sort of counterintuitive it is. Aristotle had a different sense for why things move. Impetus. The idea that you push something and now it's able to move for a while as though you're still pushing it, and then it stops. No, not right. The real story is this inertial story. Things move for free. All right? Okay, so where I left off last time, associated with this, is with what's called Newton's first law, for better or worse. And I had it with very simple language. The law is this, that an object that is free of external influences, and this is simple language, we'll do better, free of external influences, moves in a straight line at a steady pace, or covering equal distances in equal times, same idea. And this is sort of observing that inertia works. So if an object is free of external influences, it is now covered by this law. This law describes its motion and says that it moves straight line, steady pace. Not everything fits this law, and those things they're not inertial. They're not covered by inertia. If they are covered by inertia, that is, they fit the law, they have no external influences on them, then they follow the law. I often use the word inertial. Something is inertial. It means that it's obeying the law. It's obeying law. No, it fits. The law fits it. There are no objects that truly perfectly fit the law, because getting completely free of external influences, it's just really hard. Okay, but there are objects that are pretty close, and skaters are pretty close. If you want to do better, get away from the Earth with its gravity, get away from the solar system with its gravity. We have some humans have sent out a couple of spacecraft that have gone way outside the solar system. I think the Voyagers. There's the Voyagers and Pioneers. I forget. They are really out in deep space at this point. They are moving. They continue to move at a straight line, at a steady pace. They're pretty much free of everything. There's almost zero air resistance. There's certainly no simple friction. There's very little gravity. They're about as free as objects as we've ever created. And off they go. They're moving straight and true, steady as a clock. And it's all inertia. Okay, but can we do better with the language? Use the word chicken in a sentence. Yes, we can have fun and games, but also, does something like a motor move a car? Or is it just the influence factors like friction? The world has these complications around like a car. A car, in principle, if you got it started on level ground in the absence of air resistance, you got it going, and that's another issue we're going to come to shortly. And then turn off the engine, turn off everything, and no brakes, just let it go. It would go straight and true, steady forever. So you could get started towards San Francisco, and woo, it'd be a while. You get there, okay? In reality, here on the surface of the Earth, we got problems, complications. There are some frictional effects around as a car rolls forward on the pavement. There is air resistance. What other things? The hills and valleys, ooh, there are complications. You pick up speed going downhill, lose speed going uphill in interesting but complicated ways. So we don't get to do that. We don't get the pure coasting in the real world because of nuisance effects. So you need to have the car engine or motor keep going. It has to keep obtaining forward pushes on the car to compensate for backward pushes that are unavoidable, like air resistance. Okay? So language, to try to clarify the language or clean it up for Newton's first law, I've got 5 physical quantities to convey to you. So what's a physical quantity? It's a measurable amount of something that describes some particular physical process. 10 pounds is a physical quantity. 100 miles an hour is a physical quantity. 3 turns per second is a physical quantity. Okay, so we'll be going after those. And there are 5 of them that I wanted to deal with, and I'll just tell you in advance. They're right out of the book, in effect. Position, velocity, acceleration, force, and mass. So that's what we're going to do, and I'll try to do justice to them fairly quickly. But ask me if I leave things unclear. Okay? So my goal in doing this, this initial goal, is to looking at that Newton's first law and saying, external influences. What the heck are those influences? And if an object that is inertial, that has no external influences, is moving in a straight line at a steady pace, is there a better way to say straight line at a steady pace? So those are the 2 agenda items on the short term. Okay, the first one is, the first physical quantity I'll go after is one known as position. In English, at least, it's called position. The name literally isn't crucial. It could be called location, but it is, by convention, people call it position. So I have a position. And the point of having a position and knowing the position is you can tell somebody where something is, like, where am I? And I happen to be, obviously I'm right here. I know where I am. But if you want to tell somebody on the telephone where I am, you want to tell them my position. So how do you do that? Well, you need a couple of things. It turns out that the physical quantity known as position, it has some little complications to it. First off, you need a reference point that everybody agrees on. Because if you've got no reference point, there's no way to tell someone on the phone anything about where something's located, because it's always going to be relative to something that we all agree on. So my historical reference point, it's always this knob here between the 2 monitors. If that's location 0, the origin, the reference, then I am a certain distance away from that. And that's a lot of useful information. I am currently 2 meters or 6 feet. If you're more comfortable with 6 feet, fine. From the reference point, that's about 2 meters. I'm pretty cavalier in this class about the units that we use to describe things. The American system uses a whole bunch of units that are now sort of archaic, and we live with them, and they're never going to go away. And so one of them is the foot. That's about a foot, right? And other units like the inch, which is about like that, and the mile. Okay, they're perfectly good units. There are reasons why they're not as good as some, but okay, so that's a foot. Most of the world uses units that are somewhat more rational, really, because they're all factors of 10 of each other and built on each other. They're really thoughtfully created, whereas the American units are kind of a muddle. So the standard unit of length in the metric or System International, the SI system, is about that. That's about a meter. All right? If you don't remember it, who cares? I mean, I care, but not a lot. Okay? So anyway, I am about 6 feet, or maybe close to 2 meters away from that knob. So my location, you could tell someone on the phone, you know, the guy at the front of the room is 6 meters away from the origin. 6 meters, 2 meters. 2 meters away from the origin, right? I'm not through the wall, okay? Not quite enough information. You also have to tell the person which direction you go from the origin to get to me. That is, this is 6 feet, or 2 meters. So is this. And we've got to get rid of that ambiguity. And the way you do that is with a direction. You say that he's 2 meters, I got to stick with one. T's 2 meters. He's 2 meters away from point 0 south. That happens to be south, pretty much. So now you tell the person on the phone, assuming they know what the origin is, we all agree on it. They've been here, they visited once, and they know where the origin is. They know exactly where I am. So position is a quantity that requires 3 pieces. It requires an agreed upon reference point. It requires a distance from that reference point, and it requires a direction from that reference point. All right? That makes position a physical quantity of a certain type. It's called a vector quantity. You've heard the word vectors before, and they're like, oh no, panic. We're in geometry land or something like that, okay, or I don't know, or worse. Don't get worried about the word vector. It just tells you that this is a quantity that has more than just an amount. It's not like 5 pounds. 5 pounds has no direction to it. 5 pounds is 5 pounds. That's actually a slight oversimplification, but one of my challenges is that as I try to convey stuff to you, I'm aware of all the complications that show up, and sometimes they come and get me. But I will try not to get too caught up in the complications. 5 pounds is good enough as a quantity with no direction. Position has direction, and so it's called a vector quantity. Quantities without a direction are known as scalar quantities, S-C-A-L-A-R. I will never require you to know those names, vector, scalar. They're just, mathematicians and scientists needed names for these kinds of ideas. So position is a vector quantity. And it turns out 3 other quantities I'm going to present today are also vector quantities. One of them is a scalar, has no direction, mass. Okay, so position is a vector quantity, tells you where something's located. Questions about position? Right now, it's not particularly useful for that Newton's first law, but it's a start on the path. Well, if I'm an object at rest, staying at rest, my position is the same now as it is now, as it is now. But that's kind of boring. So let me get moving. And if I'm moving, which I am now, my position is changing with time. And I could keep reporting on the telephone where I'm located by telling you the position, but there's another way of doing that. I could say where I started from, and I can then tell you how my position changes with time. And there's another physical quantity that describes how position changes with time. It's called velocity. Another familiar word, but let me pin it down and make sure it's clear to you all what velocity is. Velocity is the rate at which position is changing with time. For those of you who have had calculus, and that's a lot of you, although you secretly will pretend you didn't, velocity is the first time derivative of position. Simple as that. I mean, calculus is often taught out of context of anything in the real world. The completely obvious thing to teach time derivatives in the context of is position and velocity. Okay, I will set that harangue aside and go back to velocity. To see my velocity, or what is my velocity? My velocity right now, it's how fast I'm moving. That is what distance I'm traveling every second. So it's a distance per time. 1 foot per second. That's my speed. Okay, and I'm going to run out of room, but I got started on it at least. So velocity is how far you're traveling per unit of time, and in which direction you're traveling. Because this is 1 foot per second, and so is this. So to pin them down, to tell somebody on the telephone which you're doing, you have to tell them it's 1 foot per second to your right or west. Okay? There is a reference point issue in this one too, but I'm not going to pursue it very much. So velocity is an amount and a direction. It's how fast you're moving, which is a distance per unit of time, and it's a direction, which way you're moving. So it's another vector quantity. All right, and it is not the same as position, but it's very closely related to position. It is the rate at which position is changing with time. And as one of my sort of interesting notes is, you can observe an object's position with a single glance. So you can just go blink, look at me, and realize and know exactly where I am. Positions, pin it with one measurement. To know my velocity, you have to make 2 measurements, 2 glances. You have to look once, and then again, and you say, I moved this far in 1 second, that's my speed, and I went that direction, that's my direction. So it takes 2 glances to get velocity. Okay? So thinking back to Newton's first law, it ended in my original rendition as moving in a straight line at a steady speed, or covering equal distances in equal times. Moving in a straight line means the direction of travel is always the same. And covering equal distances in equal times, or alternatively, moving at constant speed means, the speed is never changing. So velocity, which, if I didn't say it explicitly, velocity consists of speed and direction of travel. Speed is just the amount part of velocity. So an aside, and I apologize for doing the sides and not keeping a single linear path through everything, but I am what I am. Speed and velocity are not the same thing. They're used interchangeably in common language. You talk about speed when you're being casual, and you talk about velocity when you're trying to be pompous. Okay? They're not the same. Velocity has more information to it. It's not only your speed, but which way you're going. So here's the thing. That's how they are. So if you look at an object that is moving at a steady speed and a steady direction, they're moving with a steady velocity, or as physicists would say, a constant velocity. So Newton's first law, says an object that's free of external influences moves at constant velocity. Awkward side note is the constant velocity can be 0, and physicists are perfectly happy with that, and you all, I hope, will be okay with that too. Currently, my velocity is 0 and staying that way. I am an inertial object right now. I'm free of external influences, which we got to pin down a little more, and therefore I'm moving at a constant velocity that happens to be 0. All right? So we made some improvement already in Newton's first law. We got a little bit more territory to cover. And the next thing to do, rather than look deeper into velocity, let's look at those influences. What are those influences? And I've already sort of said a bit about them. They're the pushes and pulls of the world around us, technically known as forces. So, obviously not the force be with you forces, but when you push on something like that, okay, I did, push, I'm exerting a force on it. It's just a fancy name of saying it. And so forces are how hard you push, the force you exert on something, the force I exert on this ball here is how hard I push, so I push it like that hard, but that's not quite enough information because I can push it like this, same hard, but different direction. So direction matters too. Forces are yet another quantity that has, physical quantity that has an amount, how hard you push, and a direction, which way you push. And the direction matters. So obviously forces are another vector quantity. Okay, and with having brought up the term forces, I can give you Newton's first law in all its glory officially, and that is that an object that is free of external forces moves at constant velocity. And you can change some of the words here and there. It's not Shakespeare. It's not elegant language. It's just an observation of the way the world works. Okay. I will add a detail to that an object that's free of external forces moves at constant velocity. It turns out an object that has no overall force on it, or what's known as a net force on it, moves at constant velocity. Now, why did I add that complication? It's because most things in the world around us are experiencing multiple forces. If two people are fighting over me, one's pulling to your left, one's pulling to your right, they will affect my motion, but they don't do it individually unless I'm being drawn and quartered. Yeah, fun. Okay, I will respond to the total force they exert on me. So if one of them, this person pulls harder, that person's going to overwhelm the other one. I'm going to respond to some extent in the direction of the stronger or harder pulling person. So when looking at the net influence on an object, you look at the various forces acting on it, always exerted by something. Forces don't appear out of nowhere. They're exerted by something on something else. If you look at all the forces exerted on, for example, this ball, it will respond to that sum. And the sum involves direction in it. So it's a complicated world potentially. To an extent, you can just intuit what the answer is going to be. If two people decide to push on this ball simultaneously, one to the right, one to the left, and if they push equally hard, in fact, they'll cancel each other's forces, right? The result, as far as the bowling ball is concerned, is like there's nothing overall influencing me. So that's a case where the individual forces are potentially large, but the net force, the total, is zero. And at this point, conventional classes will get all immersed in these force free body diagrams, and this force cancels that one, and this one's at an angle of that, and we'd get lost in it. It's just too much trouble and not very enlightening. I will trust your intuition to sort of figure out the forces. If somebody's running down the football field and three people hit that person all simultaneously and push on them, your intuition is pretty much right. You know what the net force on the running person is. You can sort of mentally add up the forces and their directions. And I think that's good enough. That said, do you have questions about the idea of a net force and how you would assemble it out of the pieces of individual forces? Okay, so the reason to yeah, thanks.
Somebody is running down a football field
Yeah.
and gets hit from two sides, but his motion is going more
Yep.
How does that affect the net force?
Okay, so the question is if one person's running down the football field and gets hit by two people from two different sides, how does his motion or the person's motion affect the person's motion may change the forces that people exert on it just because it's hard, for example, to push on something that's moving very fast away from you. So if the person's standing still and I try to push them, it's pretty easy. If they're coming at me and I try to push them, it's in all likelihood I'll push quite hard. If they're going away from me, in all likelihood I'll push weakly. However, once it's been determined how hard they push, their motion is irrelevant. The force they exert on the person will affect that person's motion. And it will affect it the same way whether the person's moving fast or slow. Is that okay? Yeah. So just as a general observation, because this is really an interesting question, one that goes, again, right after a general misconception or easy misconception, is that when you push on things, that somehow their motion affects your push. And not direct, the answer is it doesn't do it directly. It may make it easier or harder to push on the thing, but how you push on it is your choice. You can still exert a certain force on it. You just may have to be thoughtful about how you do it. And assuming you exert that force on them, it's going to affect them the same way regardless of how their motion is going. And the effect that it's going to have on them, which I'll bring up now, is it's going to cause them to accelerate. That is, to change their velocity. So if I take this ball, for example, let me see if I can pull this off. If I exert a certain force on it, its velocity will change by a certain amount. So if I'll use this, I don't want to use my knuckles. This force, it went from being motionless to moving to your left, and it's got complications because it's a string. But that push, and maybe I can do it with my little hockey puck. If I exert a certain force for a certain time on this hockey puck, time matters in this too, but for a certain time, it will change its velocity from motionless to moving to left, okay? If it was coming at me and I exert that same force, I'll make the same changes, I exert the same force for the same time, and I realize time is a surprise, but okay, it's in there. Its velocity will change by the same amount. It doesn't matter whether it's coming toward me and I push it, or whether it's going away from me and I push it, or whether it's standing still and I push it. I will cause the same change in its velocity. All right? If that doesn't make great sense yet, it's okay. I mean, as I'm saying it, I'm realizing that it can be complicated. I'll probably revisit it when we look at down the road with the Newton's laws. Okay? Other questions? So Newton's first law we've pretty well put to bed. If an object's free of net force, it's experiencing zero net force, that means nothing, basically, overall nothing is affecting its motion. It will move straight and true, steady, constant velocity. And the world's filled with things that do this. So somebody on a scooter, one of these electric widgies guys going around, tootling along on a level, it doesn't even matter if it's level ground. They're tootling along and they're going, you watch them. The velocity's the same now, they keep covering the same distance per second, and they keep going in the same direction. They're inertial. It's just, the evidence is there. Their velocity is constant. Therefore, the net force on them is zero. Or it goes both directions. If the net force on them is zero, they're going to move at constant velocity. If their velocity is constant, the net force on them is zero. They go both hand in hand. All right, and that's a lot of times we're doing that. A water skier riding along behind the boat, okay? If the water skier is going in a straight line at a steady pace, which you can observe, and you take a video of it and you look at the video and go, yep, same distance every second, same direction all the time. That person's at net force zero. And they're not changing their velocity. They're covered by Newton's first law. All right? There are all these cases. What I should do before I leave that one, having brought that one up, the water skier is subject to all kinds of individual forces. It's being pushed on by the water, both in the upward direction, because they're kind of flying on the water, which is real, and they're being pushed backwards by the water, kind of like water resistance. They got the wind in their face. They have the rope pulling them forward. It's a whole mishmash of individual pushes and forces. But when you zoom back, what's the big picture? The big picture is, overall, they're moving at constant velocity. The net force is zero. All those individual forces must cancel perfectly, and they do. So there are perfect cancellations in cases like when you're riding the escalator up to the second floor or the subway stop in Washington. You're going straight and true, steadily uphill. Constant velocity again. Net force equals zero. All right? So skater spends a lot of time at net force zero. Overall, no forces acting on him or her, and therefore, off they go at a constant velocity. Yeah?
So Newton's first law can also be reversed, and you can say if an object is moving at constant velocity, then it experiences zero net force?
Yes. So the observation here is Newton's first law works both directions. It can be reversed. That if an object is moving at constant velocity, the net force on it is zero. Yes. They go together. One equals the other, essentially. One implies the other. All right? Now, not everything is inertial. It would be pretty boring if it were. So forces, when they do show, when an object does experience a net force that's not zero, its motion changes. And the specific thing that happens to its motion when the net force on it is not zero is that its velocity changes with time. And that process where velocity varies with time is known as acceleration. Another word that's very familiar, but now we'll pin it down to exactly what acceleration means. So acceleration, again, for those of you who have encountered calculus before, it's the first time derivative of velocity. So it's how velocity is, the rate at which velocity is changing with time. And it's a little more subtle to see, and it is different from velocity itself. It is how velocity is changing. So let me show you. This is position. Where am I? Single glance tells you all you need to know. How about velocity? This is velocity. You look once, you look again, you see that I move from there to there in a certain amount of time. You know my velocity. You know which way I travel. You know how fast I traveled. How about if my velocity is changing? You now need at least 3 glances. You can use more, but 3, because you want to see I've got a certain velocity during the first 2 glances, and then during the second 2 glances, I might move faster. So let me show you acceleration more carefully. And this is, for me, it's always, and can I think this one through carefully? I am going to move to the left initially. So I'm going to have a leftward velocity early on. And I'm also going to accelerate to the left. So, in fact, let me start with no velocity. I'm going to accelerate to the left, and I'll show you with my hand, accelerating to the left. So here we go. I'm accelerating to the left. So I'm picking up. If I keep doing that, I go faster and faster and faster, and I'm gone, okay? Not yet. All right. So if I accelerate and then I stop accelerating, now I'm back to 0 acceleration. Now I go at constant velocity because I'm inertial again. So whenever I'm experiencing a net force, I do accelerate in the direction of the net force, and that means my velocity changes in the direction of the net force. If I stop experiencing net force, then I coast. So let me do one more thing. I'll leave it with you, and I'll bring it back up on Friday. And that is, my acceleration and my velocity don't have to be in the same direction. Watch what happens if I accelerate in the direction opposite my velocity. I'm going to start off accelerating in the direction of my velocity. I'm going to do it slower so I don't crash into things. So I'm going to accelerate. Here we go. I'm picking up speed to the left. I'm going to stop picking up speed to the left. Now I'm coasting. Now I'm going to accelerate to the right while I'm moving velocity to the left. I slow down. And if I keep doing it, Now I start speeding up in the other direction. And now I can accelerate. If you accelerate opposite your velocity, you slow down initially, potentially come to a stop, and then start moving the other direction. But there's a lag in the process. So the acceleration and the velocity don't have to be in the same direction. They don't have to be in the same amounts. Okay, well that's roughly right. And we'll come back to it on Friday.